Now I want you to work on this specific example. So we do 10 episodes. So we have 10 episodes. Some episodes start here in state S. And for example, in the first episode, you start in S, you take action A2. Then in the next episode, you start in S prime and you take action A3. Then S prime, action A4, then in trial 5, episode 5, you start again in state S, and in trial 9 and 10, you also start in S. And so in total, you have played 10 trials, and in each trial, you get your immediate returns, and then you get the returns that follow. So if you play here action A2, you make it a 0.2, but then you land in S prime and you get another return. And same thing here as well. Okay, so you have 10 episodes, some are longer, some are shorter, and now I want you to estimate the Q values up here, the Q values, Q of S A2 and Q of S A1. And here it is again. So we have these 10 trials, and you should compare two methods. The first method is Monte-Carlo batch. You update once after 10 trials with a total return. And the second one is batch expected SARSA, in which case you use the Bellman equation working upward, starting at the terminal state, working upwards in the graph. And if you have time, you can also compare with an online version of expected SARSA, but that's not right now. So please pause the video for 5 minutes or 10 minutes, get started, and then I will explain how we can proceed. So now let's work on this together. The way I would like to proceed is that we look here at different combinations of state action pairs, arbitrary combination. That's why I put a hat. And then we can, for example, look at state S prime A3. That would be this transition here, S prime A3. And then I ask, in which trials did we see that transition? And that was in trials 2, 4, and 8. Okay, and then we can ask, what is with S prime and A4? Well, we saw that in many trials. We saw that in trials 1, 3, 6, 7, 9. And then the state SA1. We saw that in 2 trials, trials 5 and 10, and SA2. We saw that in trials 1 and 9. And now let's start with the Monte Carlo approach. Well, we see that in 3 trials. S prime, we are in here in this first box here. Trial 2, we get a reward of 1. Trial 4, we get a reward of 1. Trial 8, we get a reward of 1. So we have a value of 1/3, 1 plus 1 plus 1, and that gives an estimated Q value of 1. So let's do the same for the next one, S prime and A4. We have a total of 5 trials, so it's 1/5, and then we have several times we found 0, and twice we found 0.5, and that gives, in fact, just 1/5. Now let's look at S and A1. would be this transition up here. S and A1 we saw in trial 5. We got a reward of 0. And we also saw it in trial 10. We got a reward of 0. And if we average this, it remains 0. Now let's look at S and A2. Here we have 2 trials. We have this trial here. We get a reward of 0.2 followed by 0. And this means that we have an average of 1/2, 0.2 plus 0.7 makes 1/2 of 0.9, so that's 0.45. And now let's do the same, but with this expected SARSA approach. Now I work backwards from the bottom of the graph towards the top. So when I estimate S prime A3, well, I have the same information as the Monte-Carlo. So I can just copy it, it will again be 1. If I estimate S prime A4, again, I have the same information as we had in the Monte-Carlo. So again, I get 1/5. I can just copy it over. Well, if I look at SA1, which was this branch up here, well, this was a terminal state. And so again, there's nothing special. The only special case is this case here, SA2. And now let's work on this. So this should be the mean reward I get immediately. And then it's the sum over all the possible actions I can take in state S prime. So A prime, P S prime, A prime times the Q values of S prime, A prime. Now, what are these Q values? Well, that's exactly what we calculated. So the Q values are 1 and 1/2, and the policy is always balanced 50% according to our assumption. So I have 1/2, and then I have 1 plus 1/5. And then I still have to add the mean reward. The mean reward, well, I've 2 trials here, but both gave me the same reward of 0.2, so averaging here is simple. So I have 0.2 plus 0.6, so this gives 0.8. And so now let's highlight these 2 results. 0.8 is what I said. The 8 did not appear. So let's write it again, 0.8. So I compare now 0.8 with 0.45, and we see that this 0.8 as a Q value for this state here, Q of S prime, for this state here, Q of S A2, that's the state we are calculating here, that this is a reasonable average. So in fact, this would be, if I assume that the branching ratios are equal, then the exact way would be 0.25 for those 2 and 1, and I have to average this. This would give 0.625. I would have to add this 0.2. So the 0.8 is much closer to the reality than the 0.45 I got from the Monte Carlo way of doing it. And why is that? Well, with the Monte-Carlo approach, up here, I only had 2 trials. With the SARSA approach, up here, I have at the beginning, for the first step, only 2 trials, but then I maximally exploit the information, the Q values of all the additional trials that touched the graph further below. To sum this up, temporal difference methods are better than Monte Carlo, and the trick is that the averaging step in TD methods, this bootstrap idea, is more efficient to propagate information back into the graph far away from the terminal states, since information from different starting states is combined and compressed in a Q value for each state action pair or a V value for each state.